Good morning students. Welcome back to the class. Today we are going to discuss about the interaction between fibers and the dyes. Last class we have been discussing about the types of chemical bonds. We discussed there are two types of chemical bonds, namely primary bonds and secondary bonds, and all the covalent bond, ionic bond and metallic bond, they come under the category of primary bonds, which is we can say very much stronger bonds compared to that of the secondary bonds, which we saw Vander Waals forces, hydrogen bonds and also the dipole induced forces. So, study of these chemical bonds, it is very much essential to understand the dye-fiber interactions, which we do in terms of natural dyeing or in terms of synthetic dyeing. Usually, all the textile technologists, they need to study about the dyeing processes that is involved. It may be a natural dye or it may be a synthetic dye. You can take a natural or a synthetic dye and you put it on a fabric and it can dye directly with the fabric, and the bonds that is formed between the dye and the fabric are going to be discussed in this class. So, the general objective of today's class is to study the interaction between fibers, polymers and dyes. So, fibers, that is polymers, this is also a polymer, fiber is a polymer, and dyes. So, this is our general objective of today's class, and the recap of previous class, if you see, chemical bonds, they are electromagnetic forces of attraction between the opposite charges. So, usually chemical bonds are formed by the electromagnetic forces of attraction between the opposite charges of electrons and nuclei, where you have electrons of negative and nuclei having the protons will be having a positive charge, or as a result of a dipole attraction also. So, by all these processes, electron and nuclei attraction or due to dipole induced attraction, you can form chemical bonds between the atoms. Chemical bond between the atoms will be formed due to this, and we can classify this based on the dye-fiber interaction as intramolecular bonds and intermolecular bonds. Intramolecular bonds for polymer bonds and intermolecular polymer bonds. Intramolecular polymer bonds, if you see, they are the bonds present within the fiber, like CH bonds that is present within the fiber, the CC bond, CN bond, all these bonds, the bonds that is present within the fiber or intramolecular bond, whereas intermolecular bonds, the polymer chains that is responsible for holding all the polymer chains. Let us take the polymer chains like this. This is one fiber and this is the second fiber. There has to be the bond that is existing between these two fibers, and this is called as intermolecular polymer bond. Interpolymer bonds may be formed between the holding the polymer chains together. This is responsible for that interpolymer bonds, and intrapolymer bonds may be covalent. It may be the amide groups, as I have told you, the amide group, nitrogen groups that is present in your dye or in your fabric such as wool, silk, etc. And even the benzene molecule, benzene and its substituted derivatives, your ether linkage, ester linkage, your hydroxyl linkage, all these will form intrapolymer bonds, the bonds that is formed within the polymer. And nitrile groups also form intrapolymer bonds, and also all these bonds are composed, as I have already told you, it may be have not only of carbon and hydrogen, it may be of composed of CC, CN, etc. So, all these bonds are intrapolymer bonds. Next, coming to interpolymer chains, as told you, it is responsible for holding your polymer chains together, and the weak forces such as Vander Waals forces, hydrogen bonds, even some of the salt linkages, cross links, everything, they come under interpolymer bonds. So, the basic nature, reactivity, the basic nature and reactivity of a fiber, it depends on the type of chemical bond, whether it is an intrapolymer bond or an interpolymer bond. Type of chemical bond that is formed in a fiber. So, this is very important that you should know what is the type of bond that is formed, whether it is an intrapolymer bond or an interpolymer bond that is formed. Next, coming to the reactions. The reactions that is taking place, this is your specific objective 1. The reactions that is taking place between dyes and fibers will come under your specific objective 2. So, the reaction between the dyes and the fibers must take into account for the various type of forces that is exerted by one molecule upon other. And if you take the dyeing mechanism, there are 3 groups. It is dependent on the 3 types or 3 groups. All the dyeing mechanisms can be divided into the following 3 groups. The first one is the bond between dye and fiber. Bond between dye and fiber owing to covalent hydrogen or other bond. This is actually a specific bonding. So, specific bonding, first you have to see whether the bond exists between dye and the fiber is covalent hydrogen or other bonds. So, this is the first mechanism. Secondly, a dye and fiber can interact by means of a non-specific bonding. Attraction between owing to ion exchange. Non-specific bonding may be due to your ion exchange or due to your Vander Waals forces. Third is it may directly dye and the fiber, the dye on the fiber, it can be mechanically retained. So, how is it mechanically retained? Can you guess how this dye is mechanically retained on a fiber? Because there will be no interaction. It can be there will be no interaction between the dye and the fiber, and the dye inside this may be due to insolubilization. What do we call as insolubilization? Insolubilization of the dye inside the fiber, or maybe due to self-association into possibly quite larger molecular aggregate following the entry into the fiber. So, this dye, it may form a molecular aggregate like this. Molecular aggregate like this. This dye, it may form a molecular aggregate and then it may enter into the fiber. So, inside the fiber, the aggregates will be held together, and then what happens when you put water to wash it, the dyes will be mechanically retained by weak forces and this will come out. So, this is mechanical retention of the dye on the fiber. So, dye, the adherence of the dye on the fiber can take place by 3 processes. One, it may be specific, where you have a strong bonds like covalent, hydrogen and other bonds. Actually, hydrogen bonding, it is considered under weak interaction, but when combined with several hydrogen molecule, it will be strong. So, hydrogen bond and other bonds, so specific interaction may take place or non-specific interaction through ion exchange or weak Vander Waals forces, or directly the dye may be mechanically retained on the fiber. So, these 3 are the 3 dyeing processes involved. Now, let us see all these 3 bonds that is formed separately. First, you have the covalent bond, which is a strong chemical force. You have a strong covalent bond where you have strong chemical forces that is responsible for dye and the fiber attraction, and mostly it is seen on the cellulose fibers having the OH group. Due to the presence of more OH group, the bonds are formed like this. Even the CC, CH bonds, all these are formed, all these covalent bonds are formed on the cellulose fibers, and when it reacts with the reactive diester, here the atoms are responsible, the atoms of the reactive diesters are responsible for the adherence on the cellulose fibers. So, covalent bond may be formed, and secondly, you can have Vander Waals forces. The name Vander Waals forces, it is due to the scientist Vander Waals. He discovered this in 1873. Vander Waals discovered these forces, therefore his name was given to the bond. In 1873 he discovered it, and here they are very weak forces, as you know. They are very weak forces. They are present between the electrons of an atom and the nucleus of the other. The nucleus of the other atom. Okay, electrons of one atom and the nucleus of the other, which is in close proximity. The nucleus must be of close proximity. So, this is how a Vander Waals force is formed, and individually these forces are actually similar to hydrogen bond. Individually they are very weak, but collectively they are very much stronger. Okay, mostly dispersed dyes having polyester, which is found in polyester and dispersed dyes when they combine. This is your dye, this is your fiber. So, here Vander Waals forces are seen. Next, we have your hydrogen bonds. We have seen a lot about the hydrogen bond in the previous class while discussing the secondary forces. Direct and bad dyes along with cellulose fibers. On the cellulose fibers, numerous hydrogen bonds are formed. Cotton is a very good example of a fabric exhibiting your hydrogen bonds, and even the wetting characteristics is studied, which will be studied in the next classes, wetting characteristics of the cotton. We will see the structure of this and the hydrogen bond that is formed on the cellulose fibers. Fine. Then coming to the salt linkages or ionic bond, the fibers mostly containing amino groups will undergo this type of bond. Fibers containing amino groups and mostly wool, silk, nylon, when reacting with anionic dyes, they form this type of bonding, salt linkages. Okay, presence of in the presence of one interesting characteristics in salt linkages, in the presence of your water or dilute acids, what happens is amino group, they become protonated. You can see the protonation of the amino group that is taking place over here. Acid dyes being anionic in solution, anionic characteristics in solution are attracted towards the positive site of fiber. So, this is your positive site of fiber. So, mostly acid dyes in anionic solution, they are attracted towards the positive site of fiber, and as a fiber forms a zwitterion or ionization, you can also term it as ionization. As it forms a zwitterion or ionization, a negative charge is also created on the fiber. So, along with positive side, you have a negative site also, a negative site, and this is responsible for attraction of basic dyes of cationic. So, basic dyes attraction is due to this. Of cationic dyes, you can have this type of attraction due to the salt linkages or ionic bonds. Last, we have your ion dipole forces, and this ion dipole forces are you can have attracting those of opposite charges. Attracting those of opposite charges, the ions in the ions in solution can exert attraction upon polar molecule. So, giving polar molecule, giving rise to this type of forces, ion forces. So, this is also a very weak force. If you see the bonding interactions, in Vander Waals forces, the bond relative strength, you have Vander Waals forces, which is a very weak bond having the relative strength of 1, and hydrogen bond, it is much more higher having 3, and ionic bond having 7, covalent bond having 30. If you see, the strength of covalent bond is very much higher when compared to ionic, hydrogen and Vander Waals forces. So, whenever there is a covalent bond, the bond will be very good between the dye and the fiber, which is increasing the dye-fiber attraction. Okay. Now, coming to the table of fibers, dyes and dye-fiber bonds, which we can give it as SO3. So, fiber, you have some dye class having affinity, also some dye-fiber bonds, types of dye-fiber bonds. So, here if you take a cellulosic material such as your cotton, jute, rayon, etc. This is semi-synthetic, rayon, etc. If you take some cellulosic material like this, the dye class which is having affinity or direct VAT solubilized dye as well as sulfur dye and also reactive dye. So all these will form bonds, and here if you use direct VAT solubilized VAT dye and sulfur dye, van der Waals and hydrogen bonds will be formed. In the case of reactive dye, you can have covalent bond that is formed. In the case of proteins or polyamides such as wool, silk, nylon, etc., when you use direct acid or metal complex dyes, ionic bonds will be formed, and when you use basic dye, then you can have van der Waals forces. Fine. Direct acid or metal complex, yes, ionic, even basic dyes, ionic bonds are formed. When you use dispersed dyes, what happens in the case of polyester? In the case of polyester, when you use dispersed dyes, van der Waals or hydrogen bonds are formed, and in the case of cationic dyes are used, then ionic bonds are formed. Here again you can have this is acrylic. In the case of acrylic, again ionic bonds are formed here, and you can have, when you use a dispersed dye, acrylic, when you use a dispersed dye, what happens? Van der Waals forces are formed. So it depends what type of fiber that you are using, what type of dye that you are using. Based on this, bonds will be formed, and if the bond strength is very high, such as covalent or ionic, then the dye fiber interaction will be stable. So whereas if it is very weak, such as van der Waals forces or hydrogen bonds, what happens? Weak bonds are formed. As a result, the dye fiber interaction is not very good. When it is good, it is good. When the bond forms are strong, when it is not strong, then the dye fiber attraction is weak. So this is about the first part of your interaction between dyes and polymers. Okay. So what we saw here is, to sum up, we have intrapolymer or interpolymer bonds that may be formed between the molecules, and this intrapolymer bonds are covalent bond. What you have as amide and other bonds form the intrapolymer bonds, even the ionic bonds, and the other bonds that is discussed over here are interpolymer bonds. We saw the characteristics of all these bonds, as well as what are the three nature that need to be discussed between dye and the fiber that is needed for a dye fiber attraction, and also we saw the relative strength of the bond, followed by what type of dyes should be used for the fibers such as cellulosic, protein, polyester or acrylic, and the type of bonds that is formed. Okay. Now, thank you for this session.